Now, let's talk about the impact of the pulse width parameter on testing. Generally, a measuring range that is 1.2 to 1.5 times the actual length of the object to be tested is selected for testing. This is because it allows the curve to be displayed in a better proportion on the machine's screen. Currently, we have a 3-kilometer fiber connected. 1.5 times of 3 kilometers is usually between 3-something and 4-something kilometers, so a 5-kilometer measuring range is more suitable. Let's try using the minimum pulse width now. From the test results, we can see that there is a strong reflection at the end, which indicates the end of the event, and it is at the 3-kilometer mark. However, the entire fiber signal has completely dropped below the noise level. This is because we are using the minimum pulse width. Although the minimum pulse width offers high resolution, it does not have a large enough dynamic range, so it cannot generate a good test curve. Now, we can gradually increase the pulse width. A larger pulse width will result in a larger blind zone, but it enables testing over a longer distance. As we can see, the curve has started to rise slightly, and the noise is also decreasing, but it enables testing over a longer distance. As we can see, the curve has started to rise slightly, and the noise is also decreasing. Let's continue to increase the pulse width. Now the curve has completely risen above the noise level, but it is still some distance away from being smooth, so we can keep increasing the pulse width. It can be observed that the curve is still very rough. In other words, it is not a smooth curve. For longer optical fibers, a larger pulse width is required for testing. With ADNS, we have now obtained a relatively good curve result. Regarding pulse width, we are now testing a curve for a combination of a 10-meter and a 5-meter fiber. Let's try using the minimum 5ns pulse width first. On the curve, we can see a high reflection peak, which generally indicates the end of the optical fiber. Then, there is a third point at the 15-meter position, and a fourth point approximately near the 30-meter position. That means the latter segment is the ghost of the previous segment. By combining the curve and the diagram, we can make a judgment. There is a connector added at the second point, which is the 10-meter position, and a 5-meter optical fiber is connected after the 10-meter. Let's see what happens when we increase pulse width. The middle connection event gets submerged. In short, smaller pulse width means higher resolution. Does that make it clearer?